Good morning, students. We have today 8th lecture for way optics, and this is second lecture for polarization. In last lecture, we defined what is called polarization, what is polarized light, what linear polarization, plane polarization. Okay, and when a light passes through or transmitted through the polarizer, then what is the intensity? If we put one more polarizer, then what is the intensity? We also discussed Malus law. In today's lecture, we discuss polarization by atmosphere. So this is our sun. Sun emits unpolarized light. So this is unpolarized light. You can see that these are the vectors parallel to the plane and dot shows perpendicular to the plane. So up to here it is unpolarized light. So this is unpolarized light. When it enters, light enters in the atmosphere, there are so many atmospheric particles. So when this light falls on that, it interacts with the particle and scattering occurs. You know the word scattering. We already discussed in ray optics what is called scattering. When scattering occurs, then something is happening. What is happening? So when this light incident over here, electron starts oscillation because in all the particles there are electrons, and these electrons are oscillating because of both the vector perpendicular as well as parallel. But when scatter light, if you see, this is 90 degree, as you can see, this is 90 degree. So in parallel vector goes away directly and perpendicular components only scattered perpendicularly. So when you see here, then we get only electric field vectors which are perpendicular to the plane. Okay. If you put analyzer here, that you can check also. If you put here one polarizer, it is function is like it analyzes the light, so it is analyzer, but it is polaroid only. And you rotate it, ધારો કે લાઇટ ઉપરથી આવે છે અને હું પોલરાઇઝરને ફેરવું તો intensity becomes maximum and zero. Maximum and zero. It means that incident light is polarized light. Okay. So our atmosphere also makes polarized light because emission of the electromagnetic wave because the oscillations of the electrons. And when electrons oscillate, only perpendicular components are emitted toward the observer while parallel is not emitted toward the observer, and you can check with the analyzer. Okay, so we summarize this. The light from the clear blue portion of the sky shows a rise and fall of intensity when viewed through the polaroid, as I discussed here, when it rotated, because sunlight which has changed its direction on encountering the molecule of the earth atmosphere. This is called scattering. This is as shown in the figure. So here scattering થાય છે. Okay. The incident sunlight is unpolarized. આજે unpolarized છે. The dot stands for polarization perpendicular to the plane of the figure. The double arrow shows polarization in the plane. તો બે પ્રકારના અહીંયા અને dot. Under the influence of the electric field of the incident wave, the electron in the molecule acquire component of motion in both this direction. આમાં electron બંને direction માં motion કરવાના છે. We have drawn an observer looking 90 degree to the direction, so it's 90 degree. Here charge is accelerating parallel to the double arrow do not radiate energy toward this observer since their acceleration has no transfer component. And આ બાજુ transverse component નહીં હોય. The radiation scattered by the molecule therefore represented by the dots. It is unpolarized perpendicular to the plane of the figure. This is explained by polarization of the scattered light from the sky. In figure, polarization of the blue scattered light from the sky is shown. Okay, તો આ એક વાત થઈ આપણી atmosphere gets polarized. So this is the thing. Next one, we are going to discuss Bristol law. It is very important. Bristol law. Bristol law. This is one more method to get polarized light. So here in the figure, this is transparent medium, a light incident. This is unpolarized light. Unpolarized light is coming from some source and it is incident over here. Then there are two phenomena are taking place. One is reflection, other one is the refraction. One is reflection, other one is the refraction. So when this reflected ray is seen carefully, then it is observed that very few parallel components are reflected and majority it contains perpendicular component. And this parallel component, parallel to the plane, varies if you change this incident angle. જો આ ઇન્સિડન્ટ એંગલને આપણે ચેન્જ કરીએ તો આ પેરેલલ કોમ્પોનન્ટમાં ફેરફાર થાય છે. And one more thing it is observed that if this angle is 90 degree, what is this? So if angle between reflected ray and refracted ray is 90 degree, then only perpendicular component of electric field vectors are reflected. Okay, all parallel components are get refracted and all parallel components gets refracted. So see, this ray is reflection and this is parallel. So જ્યારે આ parallel will not reflect, parallel component will not. ક્યારે? જ્યારે આ angle 90 degree બનશે ત્યારે. Okay, this is the thing. In NCERT book, this is not mentioned. Sigma component is called perpendicular component and pi component is called parallel components. કદાચ તમને ખબર ક્યાંક નામ આવે તો ગભરાતા નહીં. Sigma component, perpendicular means sigma. This is a sigma components and parallel component is called pi components. And almost 15% sigma components. અહીંયા કેટલા હશે? તો 15%. 15% are reflected. 85% તો અહીંયા આવવાના છે. સમજો, 85% sigma and 100% pi. અને 100% પાય અહીંયા આવશે ને 85%. એટલે here intensity is very high compared to this one. આ intensity ખૂબ ઓછી હશે, but it will be polarized. It will be polarized. 100% pi component નહીં આવશે. Pi means parallel component and 85% component, that is sigma component. It is called perpendicular component. એ reflect થશે. 15% only reflect થશે. એટલે અહીંયા આગળ we get the polarized light, but at the same time intensity will be very less. If you do calculation, this is 7.5% intensity અહીંયા આવશે અને 92.5% શું થશે? રિફ્રેક્ટ થશે. આઈડિયલ સિચ્યુએશનની વાત કરીએ તો. ઓકે, તો આવું ઓબ્ઝર્વ કરવામાં આવ્યું કે જ્યારે 90 ડિગ્રી એંગલ બને ત્યારે we get only perpendicular, means it is plain polarized light. તો આને આપણે શું કહીએ? plain polarized light કહેવાય શકાય. Based on that, if we can derive Bristol law also. So this is, suppose angle say IB. So this is also IB because angle of incidence is angle of reflection. So So we applied Snell's law here. So mu is equal to sin IB upon sin R. This angle is supposed reflected in R. Okay, this angle is we say R. So what is R? Okay, sin IB upon sin, you can see this plus 90 plus IB is equal to 180. IB plus R plus 90 is equal to 180 degree. And then what is R? Okay, 90 minus IB. So I can write it this way earlier. So we get sin IB upon this is 90 minus IB. Okay. So this become cos IB and this is tan IB. Okay. So this is the refractive index with respect to R, and this is sin tan IB. This is called Brewster law. Sorry, this equation is called Brewster law. This is Brewster angle or angle of polarization. Angle of polarization. Okay, if outside is not there, then you have to use relative refractive index. So when we reflected ray or refracted wave becomes plane polarized, at that time tangent of incident angle is equal to refractive index. This is called Brewster law. Equation ને શું કહેવાય છે? Brewster law કહેવાય છે. Okay, so we see the theory again. તો તમને idea આવી જશે. Explain polarization of light by reflection and write the Brewster law and get the formula. The scientist Malus discovered that reflected rays partially plane polarized when light rays incident on the surface of the transparent medium and refracted ray is also partially polarized. આ મેં તમને વાત કરી હતી. ગમે તે એંગલ હોય ત્યારે state of polarization reflected ray depends on the angle of incident. આ એંગલ હું બદલાવીશ એટલે અહીંયા આગળ સ્ટેટ બદલાશે, આ proportion બદલાવાનું છે એ આપણે વાત કરી. When a ray of light incident on the surface of the transparent medium at some definite angle, કોઈ ચોક્કસ એંગલ બને ત્યારે reflected ray is found to be totally plane polarized. આ ચોક્કસ એંગલ આવું બને છે. Okay. In this state, all the light vectors in the reflected ray of light are parallel to each other and perpendicular to the plane. બધા perpendicular વચ્ચે આ બધા કેવા થશે? Disappear થઈ જશે. બરાબર છે? Okay, to each other. This is called sigma component since it contains 15% component incident. આ જે છે લાઈન લીધેલી છે એ તમારી ટેક્સ્ટમાં નથી, એનસીઈઆરટી બુકમાં નથી, પણ તેમ છતાં આમાં આપણે ઇન્ક્લુડ કરી દીધેલી છે. And 85% sigma component refract થશે. All pi components also refract થશે. When a ray of light is incident on the surface of the transparent medium at some defined angle of incident, reflected is found to be totally plane polarized. કોઈ ચોક્કસ એંગલ, એ એંગલને શું કહેવાય છે? Angle of polarization. This angle is denoted by IB or theta P. અને આપણે IB કહીએ તો theta P કહીએ. And we can derive this formula. We already derived. So what is the Brewster law? When a ray reflected from a surface of transparent object is totally plane polarized, the tangent of the angle of incident is equal to refractive index of the material of the object, and this we are talking for the absolute refractive index because it is placed in the air or in space. If it is placed in some other medium, then we have to use relative refractive index. And also we can connect it with some critical angle also. So mu is equal to 1 upon sin C. Do you know this? And is equal to tan IB. તો એક interconnected formula કે mu આપ્યું હોય અને IB શોધવાનું કે or C આપ્યું હોય અને you can calculate IB or IB માંથી C. તો આ એનો આપણે ઉપયોગ કરી શકશું. ઓકે, તો આ આપણું થિયરી વાળો પાર્ટ છે અહીંયા આગળ. અને આગળ જે થોડું છે એના યુઝ ને બધું એ તમે મેં ઘણી વખત તમને કહું છું કે લાસ્ટ પેજ તમારે ખરેખર રીડ કરવું. લાસ્ટ પેજ બિગિનિંગમાં તમારે રીડ કરો કે એમાંથી ક્યારેક ક્વેશ્ચન આવી જતા હોય છે. ઓકે, So here example 3, that is illustration. Two slits are made 1 millimeter apart. So distance between two slits is called small d. It is equal to 1 millimeter. So we write in terms of meter, point, or I can write 10⁻³ meter. Place at 1 meter. So distance d is equal to 1 meter. What is the fringe separation when the blue-green light is incident? So wavelength is equal to 500 nanometer. I convert into meter, -9. So what is the width of fringe? That is to calculate beta. So according to the formula of width of fringe, beta is equal to lambda capital D upon small d. So we put the value 500 into 10⁻⁻⁹. D is 1 meter divided by 10⁻⁻3. So this comes out to be 500 into 10⁻⁻6. This is in meter. So we can write in terms of millimeter or micrometer. So this is 500. You can say the micrometer. Okay. 500 micrometer. So if you multiply by 200 minus 6, okay, this is micro. If you want to write in terms of millimeter, then I can write this is 500 I convert this in millimeter. So millimeter में convert करूँ तो शू करूँ पड़े हमारे. So this comes out to be 500 into 10⁻⁻³ millimeter. So it is 0.5. Sorry. 0.5 millimeter. Yes. 0.5 millimeter. Okay, that is your answer. That is your answer. What is the effect on the interference fringes in the young double slit experiment due to each of the following operation? તમને એમ થાય કે આવા ક્વેશ્ચન્સ તમારે કેલ્ક્યુલેશન કાંઈ નથી, પણ આ લોજિક બેઝ ક્વેશ્ચન બહુ પૂછાતા હોય છે. તમારે ગણતરી નથી કરવાની હોતી, પરંતુ જો તમે સમજાવો તો આન્સર તમે ઇઝીલી આપી દો અને યુ કેન સ્કોર વેરી ગુડ માર્ક્સ. The screen is moved away from the plane of the slit. તો યંગના ડબલ સ્લિટની અંદર આપણે આવું હોય છે તમને. And here is one slit and here is the screen. Okay, so here with the central max bright fringe. હવે આનો જો દૂર લઈ જાઓ તો આપણી ફોર્મ્યુલા છે બીટા ઇઝ ઇક્વલ ટુ લેમ્બડા ડી અપોન ડી. આપણી ફોર્મ્યુલા છે લેમ્બડા ડી અપોન ડી. So if we take screen away from that, then what will happen? D will increase. Okay, width is proportional to D. તો પહેલો આન્સર શું આવશે? width વધશે. width will increase. Okay, width will increase, but angular position will not change. Angular width will not change. Remember, source is replaced by another source of shorter wavelength. તો અહીંયાથી તમે કહ્યું કે it is proportional to lambda. તો જો lambda આપણે નાનું રાખીએ then it will decrease. It will decrease. The separation between the two slit will increase. હવે પાછું આને કહીએ તો proportional to 1 upon d. તો ઇન્વર્સ પ્રોપોર્શનમાં છે. આને ઇન્ક્રીઝ કરીએ તો શું થશે? ડિક્રીઝ થશે. Okay, it will decrease. The source slit is moved closer to the double slit. તો આ સોર્સ છે, this is S1 and this is S2. this is your slit. Whatever we are get the fringes, this is not discussed in the text, so be careful. Be careful what I am going to discuss. S upon S. What is S? Okay, width of source slit divided by perpendicular distance of source slit to plane of S1, S2. And this distance from here to here is called capital S. This must be less than lambda upon D, where D is the separation between the two slits. So this is small d. Okay. So this is the condition to get distinct fringes. જુદી જુદી ફ્રિન્જ જોવા માટેની આ કન્ડિશન છે. S upon S is less compared to this one, or this is greater than this one. તો હવે શું કહે છે? If the separation in source slit is move closer, આને નાનું બનાવે. If make smaller, તો this will increase. So if S upon S, small s upon capital S is comparable to lambda upon D, then one cannot see distinct fringes. આ એની કન્ડિશન છે. એવું થવાનું કારણ કે સ્લીટ જ એટલી બધી નજીક આવી ગયેલી છે, તો સ્લીટ ઇઝ વેરી ક્લોઝર. અહીંયા આને હું નજીક લઈ આવું છું, તો અહીંયા આગળ જે મને ફ્રિન્જીસ મળવાની છે એ ઓવરલેપ થઈ જાય એકબીજા પર. યુ કેન નોટ સી ડિસ્ટિંક્ટ ફ્રિન્જીસ. આ એની કન્ડિશન. ધીસ ઇઝ નોટ ડિસ્કસ ઇન ધ ટેક્સ્ટ પાર્ટ, સો રિમેમ્બર ધીસ પાર્ટ. The width of the source slit is increased. આને હું વધારું છું, S વધારું છું. Again same condition is arises કે જો small s વધારી દઉં, again you get same condition. You will not see the distinct fringes. The monochromatic source is replaced by the source of white light. તો શું થશે? Monochromatic એટલે single wavelength, એની બદલે white હોય તો શું થાય? At the center there is no change at all. કારણ કે for all the wavelength, monochromatic, it contains 7 different colors and it gives construct interference here, so there is no change, it will be bright only. But at different position, different wavelength will give constructive and destructive interference. જુદા જુદા કે જુદી wavelength આપશે. તો ઉપર જઈએ કે નીચે જઈએ તેમ તમને અમુક કલર માટે કન્સ્ટ્રક્ટિવ છે, that color you will see, જેનો ડિસ્ટ્રક્ટિવ છે એ કલર તમને જોવા મળશે નહીં. તો અહીંયા આગળ તમને શું મળશે? અલગ અલગ કલર જોવા મળશે, બટ સેન્ટરમાં કેવું હશે? વ્હાઇટ જ હશે. ઓકે, તો આ એક બહુ સરસ ક્વેશ્ચન છે, થિંકિંગ બેઝ ઉપર છે આખું. સો યુ થિંક ઓવર ધેટ. ધેન નેક્સ્ટ, in example 10.3, so I already pasted here. What should be the width of each of slit B to obtain 10 maxima of the double slit pattern within the central maximum of single slit pattern? So what is the question? So this is the single slit pattern for diffraction. What is the width here? So it is 2 lambda D upon A, where A is the width of the slit. Within that how many? તો કે 10 ડબલ સ્લિટની. તો અહીંયાથી અહીંયા સુધી મારી 10 સમાઈ જવી જોઈએ. It should be 10. So what is the width here? 10 lambda D upon D, where D is the distance between the two slits and A is the width of the slit. આ બે સરખા છે. તો I write width of central maxima in single slit, color change કરી નાખું, single slit is equal to 2 lambda d upon a. Okay, and width of fringe in double slit experiment is equal to lambda capital D upon small d. Here A is the width of slit, width of slit, and here D શું છે? Distance between the two slits. In question we have given 2 lambda d upon A is equal to 10 lambda d upon d. Therefore, lambda is cancel out, dd is cancel out, એની કોઈ જરૂર પડવાની નથી. And what is here? Wavelength is જરૂર આમથી છે જ નહીં. 2 slit apart 1 plus 1 meter, એ બી જરૂર નથી પડવાની. 1 millimeter, small d is given 1 millimeter, yes. Therefore, A is equal to d by 10. So what is your d? Like 1 millimeter divided by 10. So you will get 0.1 millimeter. So sorry, 5. So it comes out to be 0.2 millimeter. Okay, so this is your answer. So width of the slit for single slit must be 0.2 millimeter. So width of the slit equal to 0.2 millimeter. Okay. Assume that light of the wavelength 6000 is coming from the star. What is the limit of resolution of telescope whose objective has diameter 100 inch? So તમે જોશો કે યુનિટ જુદા છે, તો પહેલા તો એ કરી નાખું. Wavelength is equal to 6000 angstrom. So it is 6000 into 10 raised to minus 10 meter, and diameter of objective is 100 inch. So 100 into 2.54 centimeter into minus 2. So it is 254 into 10 raised to minus 2 meter. So according to the formula, of limit of resolution of telescope, alpha, or you can say delta theta, is equal to 1.22 lambda upon d. Okay, so this comes out to be 1.22. Lambda is wavelength. Here this is nothing but actually d, or you can say 2a. આપણે ત્યાં 2a કીધું, આપણે ટેક્સ્ટ ની અંદર I write 2a. Okay, 1.22 lambda is 6000 into 10 raised to minus 10 divided by 2a is 254 into 10 raised to minus 2. So when you do calculation, you will get 2.882 radian. 882 radian. So this is delta theta. So limit of telescope is equal to 2.882 radian, or suppose it is given in degree, then 2.882 into 180 upon 3.14 degree. Okay, जे पूछा है ते. For what distance is ray optics a good approximation when the aperture is 3 millimeter wide and the wavelength is this much? So we know that this is we can determine with Fresnel distance. So Fresnel distance ZF is equal to a square upon lambda. What is here a? So a is equal to 3 millimeter. So 10 raised to minus 2 meter, and wavelength is 500 into 10 raised to minus 9 meter. Therefore, ZF is equal to a square means 3 into 10 raised to minus 2 square divided by 500 into 10 raised to minus 10. So if you do calculation, you will get 18 meter. Okay, it means that the distance less than 18 meter, one can use ray optics. Okay, 18 meter is the answer. Unpolarized light is incident on a plain glass surface. What should be the angle of incidence so that the reflected and refracted rays are perpendicular each other? Okay, when reflected and refracted ray are perpendicular to each other, at that time we can apply booster law. પણ લખવાની જરૂર નથી. At that time what we have? Okay, IB is equal to, sorry, mu is equal to tan IB. Okay, therefore what is the refractive index? 1.5. It is not written 1.5. Mu is equal to 1.5. So 1.5 is equal to tan IB, and therefore IB is equal to tan inverse 1.5. So you can see inverse of that comes out to be 56 degree and 19 minutes. Okay, so angle of incidence. So angle of incident is equal to 56 degree and 19 minutes. So this is your answer. Okay. The refractive index of glass is 1.0. What is the speed of the light? So we have mu is equal to C by V. Therefore, V is equal to C by mu. Here, C is equal to, we can write 3 into 10 raised to 8 meter per second, and mu is equal to 1.5. Therefore, we get 3 into 10 raised to 8 divided by 1.5. So it comes out to be 2.0 into 10 raised to 8 meter per second. So velocity in the glass is equal to 2.0 into 10 raised to 8 meter per second. Second question, is the speed of the light in the glass depend on the color of the light? Yes, it depends on color of the light. Okay. Velocity of light in a medium depend on color of light. Okay, so velocity is proportional to wavelength. Therefore, velocity of red is greater than velocity of the violet. That you can say that. So this is the thing.